let us continue our afternoon session. And it's an honor to introduce Andrei Okounkov, a top expert in representation theory and a vast list of related areas, mathematical physics, algebraic geometry, asymptotic combinatorics, to name a few. And today he will talk about stable envelopes for critical loci. Let us welcome.
Is that better? Okay, cool. So thank you for this opportunity, and I maybe also have to apologize to my collaborators and most of you for that. Maybe I will not make this presentation fit the profile of ICBS because I am afraid this will be sort of a rather technical talk, but without any technical details. So it's kind of the worst of the two possible worlds. But nonetheless, so in this day of age, of course, it's very important to keep your critical thinking going, but also sometimes important to take a break for it. So I want to acknowledge my collaborators who accompany me not just in work, but also in the break. So since I'm speaking in a mathematical physics session, I think it's called Mathematics of String Theory and Condensed Matter Physics, something like that. And so maybe I'll try to say words in case you're from one of these two worlds. I'll try to say a few words. What's the background for what we're doing? So physically, we're trying to compute. Well, not trying. We're computing. We're succeeding in computing with indices in certain 2+1 dimensional theories, and with very extended supersymmetry. So what does this mean? So what's an index? Index, you should imagine that you have. So this is kind of like the quantum mechanics, except your configuration space is not a finite-dimensional manifold, but rather the manifold of all possible configuration of all possible fields on a fixed time slice. So you have your fixed time is two-dimensional. We'll take it to be Riemann surface C. And you have some fields of which you consider all possible configurations, and you mod them out by some gauge theory, such as present. And so it's a huge infinite-dimensional manifold. You're supposed to consider something like L2 on that manifold. And what you would like to compute is the trace of the operator of evolution in time. So there's some evolution operator in time. And then there may be some symmetry, which is denoted by element G, something that commutes with the evolution. And then extremely importantly, if there wasn't for this minus sign, we would get an expression that contains all information about the eigenvalues of the evolution operator and the representations of the group of symmetries in those eigenspaces. But we put this minus sign. I mean, not we, people before us can simplify the problem by putting the minus sign, which makes in the presence of supersymmetry, more or less means that most of this term will cancel out, and what will be left is more or less a finite dimensional representation. Well, not exactly a finite dimensional, but something reasonable of your symmetry group as a virtual. So every non-zero eigenvalue will exactly cancel out, and the zero eigenvalues, there may still be some cancellation, but in the end, it will be sort of manageable representation of your symmetry group, and that is what we would like to compute. So in the end, the answer, there's some problem. In the answer to that is a representation of a group, or equivalently, you need to compute the trace of every element in your group. And what sort of symmetries you can have? I mean, they can both act on the space, and they can act on the field. So you should think of this my evolution. So what's written here, except I have this red arrow for G going somehow backwards. I apologize, but okay. Even when we're going in correct direction, means evolution means you come back to a certain configuration after a fixed number of. If you're tracing the evolution operator, means you want to come back where you start at our certain length of time. But if you have some element G, means you also can go to a different point in space, and you can also rotate the field. So all right. So formally, such expressions, I like indices of differential operators and so forth. They invariant onto deformations, and so we, instead of studying the ridge, so it means if you continuously vary the parameters of the physical theory, you're going to get the same answer. And so what you can imagine doing is to consider, what is called infrared, means you imagine your space is very, very big. So instead of having like a Riemann surface of a human size, it's a Riemann surface of the size of the Earth, And what will happen is that to have, computing the trace, or interested in some kind of low-lying eigenvalues, and of course, to have a small energy, you will have to be nearly vacuum at every single place on the Earth. Otherwise, you spend enormous amount of energy. So that is to say, you can describe in this limit, you can describe your theory by saying that at each point in space, I find myself in some vacuum of the theory. There is a map from my space to the space of vacuum, and the best way to illustrate is the actual weather map. So if I talk about a gas, or the gas in the coordinate system where the gas is at equilibrium, the state of a gas is described by two variables, namely the temperature and the pressure. Or if it's a mixture of several gases, then the temperature and the partial pressures. And so then if it's moving with some coordinate system, then okay, that means that you have to also record the wind. So if I want to say what's the state of the air near the surface of the Earth, then at every, like in this room, the air is more or less at equilibrium, except I kind of make it move a little bit with my gesticulation. But as these parameters, the temperature and pressure, they vary from point to point. So I have a map from my physical space, for instance, the surface of the Earth, to the space of parameters, which is the space of vacuum, space of ground states in some physical theory. So this is this is in ordinary situation. These are not arbitrary maps. They have further will be constrained to satisfy some partial differential equations. But in our situation, the supersymmetry constraints are arranged so that only the holomorphic maps contribute. So basically, you imagine that the target space is some, in the first approximation, algebraic variety or complex manifold, and your Riemann surface is also actual Riemann surface, and you study only holomorphic maps. So that's already becomes in given topological data, that becomes a fine-dimensional manifold. And on this very singular in general, but on this finite dimensional manifold, you study something like a quantum mechanics, means you would like to study something like the index of Dirac operator. Again, understood in the sense that you compute the index as a virtual representation of the whole group of symmetry, that everything that commutes with everything that preserves the Dirac operator, you want to compute that index as a virtual representation. And since representation is virtual representation means it's not an actual representation, a difference of two actual representations, because we have the trace with the sign, and not unrelated to this, you're not really computing the actual Dirac operator. You can also compute some certain virtual sense Dirac operator. So you add something, you subtract something. Yeah. So okay, that's what we would like to. That's what we would like to study, and you can criticize our intent to study it, because you would think, of all the richness of the physical universe, why did you focus on this particular small set of problems instead of studying something which somehow more relevant, more readily observable in real life? But turns out that this particular setup is, well, certainly, okay, I'm not a physicist, I'm not, or at least I'm, well, I maybe at heart, but not officially. But so this is the reason, the really mathematical reason to study this object is because they connected to so many things we know and love in ordinary representation theory, but they somehow bring it to a much wider range of possibilities. So I think, yes, we all enjoyed, or many of us enjoyed, a lecture about history and today and the next 10 years of that theory this morning. But this puts the old problems of Lie theory. This does put in the context when you're not restricted by Dinkin diagram to many, a lot more possibilities for things to have and a lot more algebraic structures to observe both in the geometric setup and study the representations also. And so, but maybe closer to life, I mean, we will, it's nice to find connection to something, to some physics which is already of a kind of a textbook quality. And what one finds here, one finds the history, I mean, one finds the theory of the quantum groups as it, so to speak, maybe not exactly in the shape that Professor Lustig described today, but rather in the shape that it emerged in well, I mean, I'm extremely flattered to see here Fyodor Smirnov, Kolya Reshetikhin, Toly Kirillov, and Igor Frankl, so many, so to speak, fathers. And I apologize, maybe I missed somebody. Yeah, I want to pay tribute to your influence on the subject. And what one finds in this case, that there maybe the most basic thing was a certain R matrix, and that the R matrix was, so to speak, the egg or the seed for which the whole tree of knowledge was growing. And what one concretely finds in this case, it finds lots and lots of interesting R matrices, and which you can interpret to be this or that or something else, and in particular you can relate them to kind of the good old statistical mechanics. So, and right, so now we would like to be a little more specific. We already decided what's our time, so the space is some Riemann surface, and we would like to be a little more specific. What's the space X to which this Riemann surface is supposed to holomorphically map? And again, so this is X was described, so far X was described as some kind of space that parameterizes all possible vacuum, that is to say, all possible ground state, all possible Gibbs state, and so on and so forth, in some physical theory. And when we talk about ground state, already implicit in that there is a certain variational problem. There has to be something, there has to be some function, I don't know, it's different function in different contexts, something like free energy, whatever, that this object has to minimize to be the vacuum. I mean, you have to be the lowest energy state, so this means you have to minimize something. But specifically in the setup we have here, this energy function in particular has the gradient square of a certain holomorphic effect polynomial function among them. So this has to be, whatever it is, it has to be a critical locus of some polynomial function on something ambient space. And a very good approximation to that is to imagine that we have a linear representation of a certain group. So that is, the group is the complexification of the gauge group. We have a linear complex representation of that group. We have a group invariant function. So on this, if you want to say stack, that is stack quotient, you take a linear representation modulo reductive group. On that you have, on that space, you have a function. You have a polynomial function on your linear representation, invariant under the group, and you'd like to study its critical. So that's the target. It's not exactly a smooth algebraic variety, but it's in some senses even easier to. I mean, in certain aspects it's easy. Okay, so that's, and so we will study. So again, we have a Riemann surface, which is the source of the maps, and then we have this critical locus, which is the target of the map, and it remains to say what does it mean to map to this critical locus. Well, there's a definition. Oh, sorry, before we go to the definition, let's consider an example. And a very rich example is already when your group is a product of general linear groups, and people usually encode this by a diagram not unlike the Dinkin diagram. So the vertices in that diagram, it's like what we saw this morning, the vertices in this diagram are the factors in So you have your group is the product of general linear group. The vertices and diagrams are the factors in this product, and the edges correspond to representation. If you have an edge connecting two vertices, or multiple edges connecting two vertices, then your representation is home from one defining representation to another. And if you have an edge connecting it to some other kind of vertices, then you have a home from the defining, either from some fixed vector space to your defining representation, or from your defining representation to some fixed vector space. And so this is your group, the product of general linear groups. That's the gauge group, and it acts on the linear representation, which is just, so if you want concrete things, it acts on a bunch of vectors, a bunch of covectors, and a bunch of matrices, when it acts on matrices both left and right multiplication, and what commutes with that is that if you have several copies of all this representation, then you can write it as it's like a home from, like for instance, if you have several copies of the defining representation, you can say it's a home from a fixed vector space of the defining representation, and then the general linear group of that fixed vector space will act. And we impose certain symmetry conditions for reasons that I'll try to explain below. And kind of importantly, in our work, the symmetry condition can be a little bit relaxed. So for this, what people call bifundamental, that is to say, you home from one to another, this cannot be relaxed. This is very, very important, be symmetric. But the other ones, there's some symmetry between the space and W that can be a little bit relaxed. And so, all right. So, right, and among this, in the class of such, so if I study, so I have if staying within this example, when I have my group is a product of general linear groups and my representation is described by a quiver, then among the critical loci of various potential or various GL invariant potential on this space, there's in particular the ones whose the critical loci are the good old Nakajima varieties, and in that special case, our theory recovers the old theory of Davesh and I, about which incidentally I think I spoke 2 years ago in A6, and then there's a similar one. Yeah. So and so this is the generalization of what you might be remembering from earlier. And then then you can ask, and there's an excellent example to which our current theory applies, and that old theory doesn't apply. It has to do with the Hilbert scheme of points on a threefold. In particular, threefold you can take a fine free space, and so Hilbert scheme of points on a surface, or Hilbert scheme of points in a fine plane. Then this is an Nakajima variety, but Hilbert scheme of points in 3 space it's not. But it belongs to this world. Means if I consider one vector space and 3 arrows going from this vector space V to itself, and I consider the potential, which is the trace of x commutator y times z, then if you take the partial in any of these variables, you'll see the commutator of the other two. So the critical locus, we have 3 matrices that commute, and 3 matrices that commute taken modular conjugation. That's basically the Hilbert scheme of points in 3 space. So so this is so if you keep in mind example, that is somehow that very much it's both motivates and sort of it's kind of like a motivated example why they have more general theory, and also it's a nice geometrically very nice example because there's this counting maps to the Hilbert scheme of points that's very, very closely related. So if you have a threefold fibered over a curve in surfaces, then counting curves in that threefold is closely related to counting maps from the base to the Hilbert scheme of the fiber. And similarly, if you only do the same in 4 dimensions, your fourfold is fibered in threefold over a curve, you will similarly be led to studying objects like that. And this continue the with my claim that these pictures, widely, I guess both wildly and widely generalize what we've seen this morning, in the sense that you can draw anything you want, declare it to be just to draw any quiver, declare it to be the Denkin diagram, and you will get some geometric object that is, in some sense, plays the role of Lie algebra associated with that Denkin diagram. The actual relation, like you want to know, how, you will get a certain Lie algebra to actually know how big that Lie algebra is. That is a slightly subtle business, and that's been only recently, for Nakajima varieties, that's been somehow finished only relatively recently. So it's a long line. There's a long line of inquiry there. So now maybe I'll, as if we didn't have enough technicalities, let me say a few words about what sort of maps do we actually consider. So we have a map to what? We have a map to to the critical locus of some function, which is what? Which is a quotient, which lives on the quotient of a vector space by group. And to be a map to the critical locus, well, I mean, it's easy. Just critical locus is some subscheme in the ambient stack. So then you just map that. But to map to the stack, well, what does it mean? That means you have a map to that stack is the same as to have a G bundle. So you have a G bundle on the curve together with a section of associated bundle of representations. That's what it means to have a quasi map, and it's stable if certain non-singularity condition. And there's also a certain technical homogeneity constraints of this potential and that principal bundle. And what will be very, very important for us? Well, I don't know. It's important for us. Whether it's important for you or not, and you'll be the judge. But for us, it is very important that so we have a. So maybe I'll write. So we have a we have some group G, which has a subgroup G gauge. This is by what we factor. So this is in our example, this is a product of general linear groups, and this corresponds to the vertices of the quiver, which factor here. And then, well, of course, it is a direct product, but you can imagine maybe it's not exactly a direct product. Maybe it's an exact sequence. There's what's it called? It's called flavor. And so in principle, you can have G bundles will allow to vary. When we compute the index, we compute the index on the moduli space. Well, this is allowed to vary. But when we compute it, we can consider further twisting. We can have a twisting by this group G, and then it means we can fix to which so a G bundle will go to a certain G flavor bundle. This we fix, and over that we integrate. So this is to have this kind of twisting. That will be very important, because this is where we will find this beautiful picture. And already this is something I owe to Igor, to Professor Frankel, Professor Reshetikhin, Professor Smirnov, and other fathers of the subject. That this is a certain Q difference equation that we will discover precisely in the setting of such twisted counts. That is to say, well, we'll see an example. And so this is again. So in our moduli problem, we have a bundle like this. This is fixed, and then you have plus a section. There's a representation. M is a representation of the group G, and plus a section of the associated M bundle over C, and that's the data. And And so on this space, one can define something like a virtual Dirac operator, and this is what the index of that we can compute. That is to say, that there is a certain coherent sheaf of which we're going to compute the Euler coefficient. And so this is the foundational things that go into defining this is spans a really long history in algebraic geometry, and I think it's one can consider it now fully completed with the 25 papers that appear here, and in this count you can further, as you count, so we have a Riemann surface C. We study maps to that X, and we can further constrain these maps by, well, it's usual. So if in any kind of curve counting theory, you would like not just count all possible maps, but you would like to constrain, like you want to count lines in projective space that meet 2 points, to mention one very complicated count. So that is to say that you would like a given point on your curve to go to some given point in space. And here the analog of imposing an incidence condition lies in this. This is why it's called critical. It lies in this critical K theory, which is the quotient of. So you have a certain polynomial function potential. Then it's you would like to. We're interested in its singularity. We're interested in where the level set W equals 0 differs from a smooth space, and one event to measure is which coherent sheaves on that space don't have a finite free resolution. And that is to say, if you take the quotient of the K group of all coherent sheaves by those which are finite complex of locally free sheaves, by perfect ones, so you get this critical K theory, which also can be related to matrix factorization, etc., etc. And it's in this group that you really find your incidence condition you would like to impose on a map. They lie in this group. And this is why it's called I don't know. I mean, why we call it critical stable envelope or something like that. So. All right. So now that I've explained how we set up the problem, one can consider our work done. Well, maybe maybe I'm already exhausted. Oh no, I'm making good time. So in fact, there is a point of view that the job of a numerative geometry is to set up the numerative problem, but sometimes people want to not just ascend to the mountain of numerative problem, but also to descend it to some, get to some actual number. So this is some starting from something like a group and a representation and a curve. We get some pretty complicated moduli space and some coherent sheaf on it. We take its Euler characteristic, get a virtual representation of this symmetry group, and it's well defined thanks to many people. But now it's a question: what is it? And if you remember anything from, well, I mean, some of you probably weren't there, and those of you who were in the audience 2 years ago, then you may remember, or with horror or some other emotions, that there is an actual computation of all these indices, but it goes through all sorts. I mean, you don't expect it to be particularly simple. You expect it to have a certain complexity to it, and it goes through some many rather beautiful intermediate representation theoretic. There's certain heavy representations here that happens, and in the end produces you this computes you this characters, computes this. And I'm not gonna show you the answer even for the Hilbert scheme C3. Although maybe I should have. Maybe anybody who wants to know, maybe we can have it in the question period. My intention today is not to give you any formulas, just to say if by some chance you've come in contact with those formulas from before, there's of course one big generalization of the other. You would expect a strong similarity, and in fact a strong similarity there is. And then, well, I guess we already had this question discussed this morning. So this is what is a quantum. So the answer is given in terms of some certain quantum group computation. And so, I mean, we heard one very, very authoritative opinion on what's a quantum group this morning. And I guess Professor Lustig's opinion was neither of the two listed here. So he expressed dissatisfaction with having generators and relations, and I fully agree with that. To me, to have an algebra defined by generators relation, it's like having an algebraic variety defined by coordinates and equations. Sometimes there's nothing wrong with that, but if you'd like to define, I don't know, moduli spaces of curves by coordinates and equations, it gets complicated. Anyhow, so you can define an algebra by generators relations, but there's an alternative approach due to this people I already tried to think many times today. And this has to do when you start with the R matrix, you use the R matrix. R matrix is a certain, in the end it's a matrix. I mean, it cannot be such complicated object. You use it as a certain seed to grow the theory of quantum groups. And this is maybe it's I think it's good to think that what I've written here, I stand by it. I think it's good to think that the R matrices were called for Nikolai, although it's slightly ahistorical, but it's a good way to explain why they called R matrices. I think it's the best thing. Okay. He exactly. His contribution should be also acknowledged. So that's yeah. Right. So this is okay. Thanks to Rodney Baxter and Fyodor and Nikolai. Anyhow, we have this theory. What's R matrix? R matrix originate. So like I said, I mean, R matrices belong to the world of 1+1 theories. They either statistical or field theories, and in the field context, they really describe the scattering of two particles. So they go along trajectories in 1+1 dimensional spacetime. They have a certain rapidities and certain internal degrees of freedom described by vector spaces V and their prime. And as they bounce off each other, there is a certain transformation in this internal degrees of freedom that depends on their rapidities, but by Lorentz invariance, it depends only on the ratio of the two rapidities. And so you get this kind of matrix depends on in principle, depends on two parameters, but in fact only through their ratio. And so they, by either miracle or definition or construction, this satisfy the property that if the three objects bounce in two different orders, the results are equal. And this is called the Young-Baxter equation. Now Rodney Baxter is finally officially mentioned. It's one of the most powerful equations. Maybe more powerful than equals MC square. I don't know. Maybe somebody will construct like a Baxter bomb. I don't know. I hope not. So it's a very, very powerful equation, and sometimes it's a miracle. But in our case, it's more or less by construction. And somehow they satisfy. We set up things so that, in some sense, checking this equation for us is in some sense a tautology. So this is. And so what's great about the R matrices? From the very beginning, they give you infinitely many operators. Namely, you have a matrix depending on parameter that acts in a tensor product of two spaces. You fix one space and call it physical. You take another space called auxiliary. In the auxiliary vector space, you take any matrix coefficient you want. This will be an operator in the physical space. And then, moreover, be an operator-valued function. And you can take any linear functional of that thing, I mean, the coefficient of some Taylor expansion, whatever, integral something, anything that takes you from functions, operator valued functions to just operators, that gives you an operator, and you can easily imagine like how many operators you're going to get. So you have, this V and V prime will be representations of your group, and so this is, you get as many operators as you have matrix elements in the representation, plus you get to choose like, I don't know, like a Taylor coefficient or Laurent expansion coefficient. So you get of the size of like a loop group in some space, and then the auxiliary representation maybe will be also by itself infinite dimensional, so it may be like a loop group of some infinite dimensional group. So it gives you lots and lots and lots and lots of operators, maybe more operators that you want, but on the other hand, in the end we need to solve a certain unity problem. So we need a rich supply of operators. So this, once you have R matrix, which you think is kind of an innocent thing, it immediately gives you a huge non-commutative algebra, really big. And this algebra, by its very construction, this is as far as I know, this is first. Is that, Nikolai? Is that first observed in that paper of yours that's in the same volume as the FRT paper? Yeah. Anyhow, it's so great to have yeah. Anyhow, so this is just this very operation. If you think about it, you can either take two auxiliary spaces or two physical spaces. So you get you either can come. In other words, these pictures you can stack in either direction, and that makes this algebra to have both product and coproduct, and they agree with each other. So you immediately get something which is basically already a quantum group. Some algebra that already has product and coproduct, and the antipode, it's like the inverse in the group. If it exists, it's unique, and if it's, and that's it somehow doesn't come up so much, the antipode in this business. So here's your quantum group. And then associated with this quantum group, there's a remarkable Q difference equation. So in general, I'm going to say that this computation of these indices go through solutions of Q difference equations, and very important mathematicians other than I, like for instance like Peter Schulze, been preaching that somehow Q difference is the new way to go, but it's also the old way to go in the sense that associated to every quantum group there's a certain remarkable Q difference equation discovered by Professor Frankel and Professor Reshetikhin, called quantum Knizhnik-Zamolodchikov equation, and of course Knizhnik and Zamolodchikov were also giants of the field. And how does it go? It's a Q difference equation, and it acts you have a representation, you have a tensor product of some spaces in which the quantum group previously acted, and what you imagine this. Well, it's kind of like if you think of this representation as worldwide of particles that run in 1+1 dimension, you have some number of them doing nothing, and one runs around everybody, and it interacts with everybody. So there's another matrix for every single crossing, and then when it runs around the cylinder, there's a seam of the cylinder. To make a cylinder, you have to take a cut of paper, and take a paper, cut it, and glue, and like that. And you glue means that you insert some operator between two pieces of the paper. And what this operator needs to do, this operator needs to commute with the R matrices in the way that's indicated on the slide. And by the virtue of the fact that the R matrix depends only on the ratio of its parameters, spectral parameters, since the R matrix only depends on the ratio, what you can do is you can impose a difference operator. If you in other words, you take your variable, you shift it by Q. So and that Q is a new variable unrelated to any other variables you've seen. You sometimes also into this, I guess, no, in linguistics talk about called V, but very often people use Q to denote some notion associated with the quantum group. This is not the case here. Q is just some completely different variable. So in other words, as you go around, in particular, you can shift by Q, and that gives you a certain canonical Q difference, flat Q difference connection on the tensor product of representation of whatever this quantum group which is constructed. So this connection was, like I said, first constructed by Frankel Reshetikhin, and it limits to the Knižnik Zemological, why it's called the quantum Knižnik Zemological. So and it's this object that we would like to find. It's this object for which we would like to find an enumerative interpretation. We would like to find an operator. So this is in the end there's a Q difference equation. And what's a Q difference equation? You have some function, you shift it by Q, and then it's a linear Q difference equation. So if you have function shifted by Q, and then you have to apply a matrix. Right? So that's so it's this matrix that we would like to have some geometric construction of that matrix. And the way so this would be, so since it's a matrix, means what? So how do you get a matrix? Matrix, you need to have like one index and the other index, which means you probably want a count, some kind of count of maps where you fix the value at one point and at another point. This way you get exactly like a tensor with two indices, and that's your candidate for a matrix. And once in enumerative geometry, it's very hard to compute, but easy to prove certain compatibility constraint. And just the compatibility for this with this one equation is such strong constraint that the rest of the theory is more or less algebraically follows from just identifying the QKZ. Because if you somehow commute correctly with the Q difference equation, means you have something that has a correct commutation with the Q difference connection, means your functions have to solve a Q difference equation. But very few things that normally appear in the world of enumerative geometries, for instance, very few rational functions solve a Q difference equation. It's extremely strong constraint to be a solution of Q difference equation, because a solution of Q difference equation usually rather transcendental function. It behaves in a way that enumerative comes in. It behaves in a way that if it's not done correctly, it's very easy to rule out from enumerative theory. So it's extremely constrained. So what sort of count we're going to take? So we will take precisely the kind of count that we were explaining here. So we want to take count maps from P1 to X, and we would like to fix the evaluation at 0 and infinity. So we'll get a matrix. So anytime I fix evaluation, I get to put an element in this critical K theory. So if I have two evaluations, I have two, something with two indices in this critical K theory, something like an operator from one to another. But in the middle, as I count these maps from P1, I will allow a non-trivial clutching functions to glue into a non-trivial X bundle of P1. So functions from a space, somewhere there are sections of a trivial bundle over C, but I can consider a section of a non-trivial function. So if I have a symmetry here, if I have a one-parameter subgroup that goes into this flavor symmetry group, I can use it as a clutching function to make a non-trivial X bundle over P1, and then now I will be studying sections of this non-trivial bundle. And so this is, again, for those of you who keep score, I don't know if probably I would have been myself completely lost by this point in the talk, but we somehow have to keep going. If you keep the score, at this point, we take a one-parameter subgroup going here. At the beginning, I said there will be some symmetry constraints on the representation of this group that can be a little bit relaxed, but this one-parameter subgroup has to go into the part of the group that actually preserves the symmetry. For that is actual symmetry. And that's yeah, then you'll get a difference equation of the form. You take some function, you shift it by 1, and it equals itself. Yeah, so yeah, it can be trivial. Yeah. So this is a matrix of a Q difference equation. It's an equation of unknown element on on this critical K theory. The critical K theory for the Hilbert points A3 is this vector space of the size of how many three-dimensional partitions there are, and in that space there are certain metrics which we will find to be this QKZ matrix for a certain quantum group. Yeah, but then it'll be just sort of, yeah, then we'll just get, at that shift operator, we'll just get the identity. What I'm explaining here is the shift operator. And the shift operator for trivial shift is the identity. No. This is just this is like the glue matrix, which you take out of the operator anyway. Yeah. This looks like, so this trivial shift will give you will give you no difference equation. You know, like what's a shift operator? You have to have for the cube C2. You have to have a non-trivial bundle over your curve. No. Then you have to. It's something else. It's. I mean, in some sense, in K theory it isn't. So in K theory it's something else. If it's in K theory, if you just have 2 points, it's something called glue matrix. It's like a bilinear form, which you use this bilinear form to turn this bilinear form into an operator. Yeah. So this is again. So we count them. So we count everything. We do all these counts occurring with respect to all these symmetries. And like I said, since we put evaluation on 2 sides, there is it's like an operator from critical K theory to critical K theory. Except of course we record. Did I mention that we wait? So you know, the spaces of maps, they're fine dimensional only once you fix degree. So this is, we have to sum over all degrees and put this marker z degree in that count. They not just operators, they're operators that live in formal power series in some variable that keeps track of the degree. The important point that I want to say is that the equivariance, since you have a non-trivial, so we have a non-trivial X bundle, the equivariance is different in the source and the target of this map. So there's a different equivariance in the source and the target. This is why it's called the shift operator. Shift equivariance by precisely this co-character C. And the very, I don't know if you somehow have any appetite for that, but the key point about that is that in this twisted geometry there are many different constant curves, and constant curves can have different degrees. So because so it's like if you have consider, I don't know, non-trivial P1 bundle over P1, like I don't know, like this surface. This will have this kind of like a constant section. That's another constant section, and they have different degrees. Same thing here. It says so there will be different constant maps correspond to different components of the fixed locus of sigma on this X, and so that they will have different degrees. And the statement that this what we prove, so this is one of our main theory, we prove that this operator is the QKZ, and the QKZ when you can imagine the really important case of QKZ is when you take all these arrows and unite into one big arrow, one arrow. So you just have one R matrix that goes around, and so that we have it's this operator that is that count, and what's extremely important about that, when we're setting up this count, it's we count curves with all possible degrees, and we put this marker z to the degree to sum up the curves of all possible degrees. But in the end, the whole complexity of the equation is in this R matrix, which has no such variables in it. And that is to say that that if you write this problem, if you use the R matrix to reformulate the problem a little bit, that only the constant maps contribute to the count. It's not true. It's not true as such, but in some way with slight modification, you find that only constant maps contribute to this curve count. But the constant maps like we discussed have different degrees, and so it's not trivial, it's not stupid. It gives you a non-trivial thing. But in the end, you show that after a certain rearrangement, you only pick up contribution from the constant map. And this is why, this is why having no shift will not work, because you'll just find a scalar operator. That's somehow not good enough. All right, let me skip most of the remaining slides. It's just basically saying that this R matrix comes from, so the title of the talk were stable envelopes in critical commode. And so stable envelopes is something that is used in the geometric construction of R matrices. It's like a half of the R matrix. And so in particular, you can think of stable envelope as giving you a certain special basis of this critical K theory. And the statement is that in this special basis, only the constant map contribute to the count to the count that defines this thing. And what it is fundamentally is it's a rigidity result. It's a rigidity result in the style of classical paper of A.T. Hirzebruch and further exploited by Krichever. And the way that the stable envelopes are set up, there are certain. So what's a stable envelope? Maybe it's a little too late in the talk to go into any kind of detail, and maybe I'll have a little bit of water. So what's a stable envelope? Stable envelope is like an improved version of the attracting correspondence. If I have one parameter subgroup acting on some space X, then you have a natural correspondence between, if I apply a one parameter subgroup and I take the limit to 0 and I go to some fixed point, that defines me a correspondence between the original point and the end point. So it's some Lagrange. It's some correspondence which, if X was, for instance, symplectic and the action was preserved in sequential form, there will be a Lagrangian correspondence. And in difference, so a lot of people use this kind of attracting manifolds for many different reasons, for construct maybe whole algebras and do other things. And the way in which stable envelope maybe offers a little bit of improvement on these constructions is that these correspondences are improved in the sense that their results are proper over X. And that's extremely important for any kind of rigidity argument. I mean, in general, somehow, if you're trying to make a geometric argument based on anything like rigidity or anything like properness, extremely important to have that properness. I mean, that otherwise it just falls apart. And so that's the other technical advantages of stable envelopes. Maybe I will not go into all of them. And maybe they constructed by a certain procedure, which I guess I already spoke about it 2 years ago, and then this is what we generalized to this critical situation. And okay, let's skip that one too, and that one too, and so so the stable envelope is what? Stable envelope is, maybe I'll write it here. Stable envelope was a map from this fixed locus, K critical of the fixed locus to the K critical of the whole thing. And then, in that sense, this is the rest of the R matrix is just gotten by just taking the transpose things going the other way. So there's either you use unstable envelope, the other going the other way, or the transpose of this operator. That's what gives you the R matrix. And so now I'd like to point one thing before it is time to start questions, but I'd like to point one thing before I go there, is that so far I spoke about our theory by sort of saying that there is a theory for Nakajima varieties, and we just put it in much bigger generality. And one thing we find in it, we were somehow, we knew we were going to find it, so it's not, but we did, is that there's one difference with this quantum group, with these quantum groups and the Nakajima variety quantum groups, and the difference lies in the fact that these are matrices, the old R matrices, the more canonical, well, whatever, the old R matrices of from textbook and the ones you find from the Nakajima variety, they have the property that their value at 0 and infinity are regular and invertible. And that is not the case here. So that is, it's okay. So it means it's okay for, if you have a pole, so be it. You can deal with it. But it just says you leave the world of quantum group and you go to the world of shifted quantum group, and that requires a certain. I mean, it's a bigger world. So if I already tried to explain that there's the world of quantum groups is quite a bit bigger than the AD whatever the Cartan. I mean, despite Killing's paper being one of the best papers in the history of the universe, we're not trying to compete with that, but still pointing out the fact that there's quite a bit more stuff there. But in this, once you go to the generality that I'm discussing here, you're forced to deal with the shifted quantum group. But which is, like I said, it's okay. It just means your R matrix can have also a singularity at 0 to infinity. And that's but that. I'm already 2 minutes into the question time, so maybe I'll stop here and then.
Thanks a lot for the talk. Any questions or comments? I feel we had some questions during the talk, and this is the end of the session. You have one. Yes.
So can you say, there was this thing you said, what was that statement that you can recover something from this Orlov's matrix factorization category?
No, I mean, just what Orlov theorem says. That says that this matrix factorization is something in the category of singularities are the same. That's his statement.
But this was in which dimension for you?
It doesn't matter in which dimension.
Okay,
it's
so
just
let me ask
you have a hypersurface singularity, and we just take this critical case here. Yeah, you can equate it to matrix factorization. I'm just saying many people like and use matrix factorization, and I'm saying we're using the same thing with in slightly different incarnation. Yeah.
Okay, so let me ask you another thing. So when you send these quasi maps into Hilbert small points in C3. Okay, so on the other side, I have to pull back to the first curve, the source curve. You get sheaves moduli space on the fourfold, right?
That's right. Yeah.
Okay, so this moduli space, let's assume that it's colonial, etc., etc. Yeah. It has a potential function. Do we have matrix factorization for that potential function? Shifted potential. That's my question. So if you have a -1 shifted potential function, my question is, do we have matrix factorization category for these kind of functions?
I think. Yeah.
I don't know it.
Yeah. I think I'll be silly for me to try to somehow compete with those guys in what they know about this question. Yeah, but So elliptic is complicated. You see, even in classical theory, elliptic, like if you want the elliptic analog of QKZ, that only works if you're in zero weight space. I mean, that's at least it. And here, while in the fine dimensional representation theory, the zero weight space is always the biggest. You can imagine, I mean, certainly there's some, if you look at how the weights are distributed in a finite dimensional representation, it's, you know, it's something concave, and zero is at the top, the biggest space. But in this space, the zero is sometimes, it's not even a weight, or the Hilbert scheme of points is the Hilbert scheme of 0 points. And so it's a question that can be you can somehow raise this question already in the good old finite dimensional GLN representation. Like can you write some meaningful equation in the weight space which is not zero? By contrast, the elliptic R matrices will appear as so they will not appear directly, but they will appear as the monitor. There's a whole business of how you compute not just the equation but also their monitor. So in general, so this is like in some kind of generality, we have this this kind of theory how you compute and they interpret the monodrome of these equations. So the monodrome of this Q difference equation you can certainly compute in terms of certain elliptic R matrices. That would be fine. And then the next step would be maybe to reinterpret these elliptic R matrices as some kind of Fourier-Mukai is what's it say, the images of a certain derived equivalences for some kind of loop groups in the K theory of the corresponding stuff. That's so that there should be also categorification of that. But, so like if you just to repeat myself, there is no elliptic QKZ as far as I know outside of very simple examples, but elliptic quantum group appear as the monodrome. I mean, certainly appear geometrically and potential representation theoretically as the monodrome of this equation.
Okay, maybe one more short question.
Can you explain what does shifted mean?
Okay. There's a very simple. I'll give you a simple explanation. So how did we get operators before? So we took some matrix element, and it was and then we took some matrix element in the auxiliary vector space and expanded it into Lorentz. But now, so previously we had some assumption. Previously we had like R of 0 was regular and invertible, which means that the negative Laurent coefficients will vanish, and the zero start with something relatively simple, and the positive, okay, something. But then if you have a singularity, it means you get some negative operators, or if you have a zero, it means some of the operators are missing. So that's that sort of thing. So you either get more or fewer operators.
Okay, I encourage everyone to continue the discussion during the break. Now let us thank Andrei again.